This is example 5-7, a turbine in a pipe. So we have a pipe with a diameter of 400 millimeters that gets reduced to 150 millimeters, and we also have a turbine sitting there at point C. And we're given the information that the turbine draws a power of 68.5 kilowatts, and we're given the pressure over here at that B, and we're given the velocity at B, and we're asked for the pressure and the velocity at A, and we're told to neglect frictional losses between A and B. So I think we can start with the velocity at A, because we can just use continuity, right? So we can say from continuity equation, and now we also know that we have incompressible flow. So with incompressible fluid, what else do we know? And we know like our control volume would look something like this. All right, so we know we have a fixed control volume. Why is it important that we have incompressible flow and a fixed control volume, right? That means that our volume is going to be constant and our density is going to be constant. That means our d rho v dt term is going to be 0. All right, so we can say for our continuity equation, it's just going to be the flows across our control surfaces. All right, so we can say in B, right, I'll just draw that in real quick, right? So we'll have the normal for my area is going to be pointing outward, the velocity is pointing inward, so that would be negative. So I have negative V, not A, but B times AB, and then of course on the other side, area is pointing in the same direction as the velocity, so that'd be plus VA times AA, and that's equal to 0. So if we solve that for VA, which is one of the things that we're looking for, right? So VA is then going to be, we'll bring this over, so it'd be AB over AA times VB. Now these are all circular pipes, so we can say that is pi over 4 times dB squared divided by pi over 4 times dA squared. That's my B over AA. And let's not forget our VB, which of course is a given, right? 4 meters per second. So the pi over 4, of course, cancels out. And we can kind of pull the diameters together, so we can say that would be dB over dA squared times VB. And so if we plug in our numbers, then our dB is 400 millimeters, so 0.4 meters. Our dA is 150, so 0.15 meters squared, and then times 4 meters per second gives us 28.444 and so on meters per second. So if you round that to 3 significant digits, we get 28.4 meters per second. Right, this would be our first result. Right, it asks for the velocity and the pressure, so we already have the velocity. Now, if we want to get the pressure, of course, we're going to go ahead and use the energy equation. So let's write that in our general form. Right, that's going to look something like P in over gamma plus V in squared over 2G plus Z in plus H pump is equal to P out over gamma plus V out squared over 2G plus Z out plus H, let's just do turb for turbine, plus our head loss. Right, that's our general one. Now we have to decide where our in and our outflows are. In this case, it's pretty easy. Right, B is of course is where we come in, so we'll say equal in, and A is where we go out. All right, so we'll have to find all these values for B and for A. All right, so the pressure, one of our pressures are given, the other one we're looking for, so that one's easy. The velocities we both have, right? We calculated the one at A and we're given the one at B. So these two and these two terms, that's to the elevation, right? So we can just say, we'll set the datum right there, right? That means we'll have both of our elevations are 0. So datum at center line of pipe. That means our ZA is equal to ZB is equal to 0. All right, where is our equation here? All right, so we have the first three here, the first three there. That means we're now left with H pump, no pump, so that's 0. Let's write down no pump, which means H pump equal to 0. Then over here, the turbine, that's what we're trying to find. Oh no, we're given the turbine. Wrong problem. We're given the turbine as 68.5 kilowatts. So don't really need to do much there. And we're told that there's no friction losses. So that's good. So we can say no friction loss. That means HL is equal to 0. So I think we have everything. Oh wait, we have the turbine. It's given, but it's given as a power, and we wanted to have it as a head. So we have to go ahead and convert that. So we can say that, of course, our turbine head, all right, we get that from our equation. The power of our turbine, let's stay with turb, right, is equal to Q, which is the flow rate, times gamma times H turb. All right, so what do we have? We have gamma, of course, it's water. Are we given Q? No, but we're given the inflow and the area. So let's figure out what Q is real quick here. Let's see. Q is going to be equal to V, let's take B because that's our given one, just in case we did a mistake with A, times AB. All right, so that would be VB times pi over 4 times dB squared. So that is then 4 meters per second and 40 centimeters. So 4 meters per second times pi over 4 times 0.4 meters squared. And that gives me 265 cubic meters per second. So that then means I can get my H turb from above, right, from the equation that we have there. So if we solve that for H turb, we'll have the power, not trub, but turb. The power divided by Q and gamma. Q times gamma. We are given that it is 68.5 kilowatts. So 68.5 times 10 to the 3 watts. Now watts are joule per second, so it's Newton meters per second. And we need to divide that by Q, which was found as 0.50265 cubic meters per second, and then times the specific weight of water. And of course that should come out as a length. Let's write down the number, and then let's look at the units. 89158 meters. So we have the newtons that will cancel out. We have cubic meters that cancel out. We have seconds that cancel out. We're left over with meters. Exactly what we wanted to. All right, so then we can go back to our energy equation and put all our things in, and then solve it for our outlet pressure, right? PBs or PAs we're looking for. So if we, it's kind of hard to see here, but like, you know, we had that P in, so that'd be PB in our case, divided by gamma, plus VB squared over 2G. Then we said that our elevation is 0 and our pump is 0. And that is then PA, which we're looking for, over gamma, plus VA, which we calculated. And then plus 0 for the elevation, plus our H turb, which we just calculated, plus is 0 for the head loss. And now let's see, we need to solve that for PA. So let's do that in 2 steps. We'll say PA over gamma. So if I leave that on one side and bring everything else to the other, that would then be PB over gamma plus VB squared over 2G minus VA squared over 2G minus H turb. Right, that's just rewriting my equation. Then I can multiply by gamma. Then I would have PA, which is the one I'm looking for. There should be a capital A there, not lowercase a. That, of course, just cancels out the gamma. Here I'll get gamma times VB squared over 2G minus VA squared over 2G minus H turb times gamma. And so nothing much to do in the front here. I have the same, oops, I'm missing a gamma there. First of all, I can pull out the gamma over 2G. I can also recognize that gamma over G is just rho. So I'll have rho over 2G times VB squared minus VA squared minus H turb times gamma. And then I can go ahead and I can start. Oop, I'm missing the, I have a G in there. We don't need the G. The G we just got rid of that one. So let's rewrite this. That'll be just over 2. Oops. Go back to pen. Right, because the G, of course, got combined with a gamma to create a rho. All right, so then all that's left is to plug in numbers. So PB was 380 kilopascals, so 380 times 10 to the 3. We'll leave it as pascals because we're looking for a pressure. Plus the density of water is 1,000 kilograms per cubic meters divided by 2. Then our 2 velocities. Let's make that a square bracket. So we'd have 4 meters squared minus the one that we calculated was 28.444 meters squared all of that minus H turb, which was 13.89158 meters, and let's not forget gamma, 9,810 Newton per cubic meters. And when I plug that in, I get minus 152,819.6 pascals, or if I go to kilopascals and go to 3 significant digits, minus 153 kilopascals. So that would be our pressure. That means we're actually below atmospheric pressure there, right? So we'll have a negative pressure at A. All right, so now we have our pressure and our velocity, and I think that's what we were asked for. We're asking to find the pressure and the velocity, so we use the continuity equation and the energy equation to find those two values.